hybridized sp orbital is going to look more like a p orbital, more lobe-shaped, okay? And if you don't know what I mean, you will in a second when we draw it out, okay? Okay, so let's draw out these three options that I just mentioned. And let's start with the simplest example and just mix one s orbital with one p orbital. Okay, so hey, let me draw out the whole collection of orbitals that we're dealing with. So we've got one s orbital along with 1, 2, 3 p orbitals, right? Okay, and if we start with the simplest example and just mix one s orbital with one p orbital, let's see what happens, okay? So, hey, let's mix one s with one p and leave these other two p orbitals alone, okay? So, hey, this is what they look like as pure orbitals, right? A pure s orbital is round and fat, a pure p orbital is long and skinny, right? But if we hybridize them, if we mix them together, the resulting sp hybridized orbital will be a mixture of the two. So it won't be completely fat and round, and it won't be completely long and skinny, it'll be a little bit of both, okay? So, hey, let's mix our pure s and our pure p orbital together and see what kind of hybridized orbital we make. Okay, so what's going on is that we mixed an s and a p orbital together to pop that out. Let's see how this happened, okay? So, hey, we took an s, combined it with a p, right? So let's lay these right on top of each other to see how they mix together, okay? So, hey, here's the p orbital. Here's the s orbital right on top of it. This popped out a hybridized orbital that looked like this. That was all big on one side and all tiny on the other. And so what happened was that when these two mixed together, they pooled all of their electrons into one side of the lobe, okay? Which is why you see this huge concentrated area of electrons and this really, really small unconcentrated area of electrons. The reason why you want to put so many electrons into one area is because, hey, when you're trying to make a bond with another atom, you want to put all your electrons into it, okay? So you don't want to be split up 50% of your electrons on the right-hand side, 50% on the left-hand side. You want to put all of your electrons on one side so that you can go into making that bond 100%, okay? So that you have the best possible chance of making that bond with the other atom. And that's why you see one big side here and one small side here, okay? Like what you see up there. Okay, so let me erase this. And cool, we see that the resulting hybridized orbital we made looks like a mixture of the s and p orbitals that we mixed together. You can see that it's still sort of lobe-shaped, right? But it's rounder and fatter too, okay? So, hey you guys, if we mixed two pure orbitals together, how many hybridized orbitals are we going to make? 2, right? So we're actually going to get 2 of these guys that look like this, okay? However many pure orbitals you mix together is how many hybridized orbitals you make. So we mixed 2 pure orbitals and we made 2 hybridized orbitals, okay? So hey, let's write that down. The number of pure orbitals that you combine, the number of pure orbitals that are combined, this equals the number of hybridized orbitals that you produce. And if you're wondering what happened to these 2 unhybridized orbitals, hey, they're still there. We just didn't draw them, right? But hey, if you want to, they're still there. There's the 2 pure unhybridized orbitals that you didn't hybridize, and this is the 2 hybridized orbitals that you made from mixing these 2 together, okay? Okay, so if I drew these hybridized orbitals, how they actually look like with respect to an atom, it would look like this, okay? So here'd be 1. Let me draw the other orbital in blue, okay, so you don't get these lobes confused. Okay, so this orbital in black that I've drawn is one orbital. This orbital that I'm drawn in blue is the other orbital, right? And hey, the nucleus would go right in the center between these, right? And the electrons would be revolving around this nucleus in these orbitals that you see. And hey, you guys, we want to draw these orbitals as far away from each other as possible, right? That's why I've got them pointing in opposite directions because, hey, the electrons in each of them will repel each other 180 degrees apart, right, you guys? So, hey, This is going to be 180 degrees away from here, 180 degrees here. Okay, so just to make sure we're all on the same page here, what are these orbitals used for? They're used to make bonds, right? This atom is going to overlap its orbitals with the orbitals of another atom. And when two orbitals overlap, this forms a bond, right? So, hey, what do I mean? Well, let's pretend that these orbitals that I drew belong to a carbon, okay? So, hey, let me just pretend that this is a carbon, okay? And these are the orbitals on that carbon. So this is a C for carbon, okay? So, hey, let's pretend this is one carbon and it's going to bond with another carbon. So let me draw another carbon here with some orbitals and we'll see how they bond. So here's this carbon. There's one of his orbitals. There's his other orbital, okay? Okay, so here's two separate carbon atoms. Let's see now how they come together and bond. And hey, you guys, how do atoms make a covalent bond? By sharing electrons, right? So if I want to make this drawing a little bit more accurate, let me go ahead and put one electron in each of these orbitals. Okay, so let me give this guy one, and I'll give this guy one, okay? And guess what? An orbital wants two electrons in it to be stable, right? Just like two shoes fit in a box. Okay, well, hey, this carbon is like, dude, I only have one electron in this orbital. And this carbon is like, dude, I only have one electron in this orbital too. We should hook up so we can both share two electrons and be stable. And this is exactly what happens. Let's draw this out. So these two atoms are going to overlap their orbitals and form a bond. Let's see how that happens. So here's one carbon. There's one of his orbitals. Let me draw the other one. Okay. Oh, and hey, don't forget the electron that this guy had in his orbital. Here's the other carbon. Here's the electron that he had in his orbital. And here's the other lobe for this guy. Okay, but check it out. They overlap their orbitals and formed a bond right here. They're now sharing these two electrons in this overlapping region. And if you wanted to represent this as a Lewis structure, you could just draw these two atoms being bonded together like this. So here's a carbon covalently bonded to another carbon. This means the exact same thing. And this is exactly what we saw in molecular orbital theory, except now we're using hybridized orbitals. Okay, another thing that I want to mention is the naming system that we have for hybridized orbitals. Okay, so hey, our naming system for hybridized orbitals depends on how many s orbitals and p orbitals you combine to make those hybridized orbitals. So hey, in this case, we combined one s and one p orbital. So we would call this sp hybridized orbital that we made, we would call this a sp. So hey, this would be called an sp hybridized orbital. And we call it this to let us know how many s and p orbitals we combine to make it. So if you want, you could also say that this is a s1 p1 hybridized orbital, okay? But the one is pretty much implied if you don't write it, because hey, we combined one s and one p to make an s1 p1 hybridized orbital. This one is just saying we used one s orbital. This one is just saying that we used one p orbital, okay? And hey, you guys, if an sp hybridized orbital is made from one s and one p orbital, then couldn't you say it's going to look half like an s orbital and half like a p orbital? Yeah, right? So you'd refer to these orbitals as having 50% s character and 50% p character. And if you want to do this mathematically, just say, for example, s character, you'd take the number of s orbitals and divide it by the total number of orbitals combined. So, hey, if you want to take or find the s character, just take the number of s orbitals you used, which is 1, and divide it by the total number of orbitals that you combine, which is 2, and this would give you a 0.5 or a 50% s character. And you can do the same thing for p character. Take the number of p orbitals you used, divide it by the total number of orbitals combined, and this will give you your p character, okay? Okay, so just to make sure you guys have this down, what would you call a hybridized orbital that was made from mixing one s with two p orbitals? S1p2, or just sp2, right? One S was mixed with 2p, so hey, you're going to make an sp2 hybridized orbital, okay? You're actually going to make 3 sp2 hybridized orbitals because, hey, the number of pure orbitals you combine is the number of hybridized orbitals you pop out, right? Okay, so how much S and p character would that orbital have? Well, since there were a total of 3 pure orbitals combined, then its S character would be 1 over 3, and its p character would be 2 over 3, right? So you would say that that orbital is 33% S character and 66% p character, okay? Okay, so hey, let's look at the shape and number of bonds that compounds have if they have sp hybridization. Okay, so hey, what's the shape and how many bonds is a compound going to have if it has sp hybridization? And as we said before, these orbitals are 180 degrees apart. Remember we drew those up? They were 180 degrees apart. And if you think back to the 3 basic shapes and bond angles predicted by VSEPR theory, what shape does this look like? Tetrahedral, trigonal planar, or linear? Linear, right? And how many single sigma bonds do these compounds have? 2, right? Of course they can have multiple pi bonds, but the thing I want you to notice is that they only have 2 sigma bonds. So compounds with sp hybridization have 2 sigma bonds, right? They are linear shaped and have bond angles of 180 degrees. So you don't have to write this down. We're going to write it down in a table later. I just want you to start seeing the relationships, okay? So sp hybridization is 2 sigma bonds, a linear shape, and 180 degree bond angles, okay? Okay, so as a last really important point, sigma bonds, or single bonds, these are made by overlapping hybridized orbitals. Sigma bonds do not form by overlapping pure orbitals. Hey, let me let you guys in on a little secret before we go on, because a lot of people don't realize this. Hybridized orbitals are responsible for forming sigma single bonds, right? Single bonds. Remember, bonds are formed when 2 orbitals overlap. Well, single bonds form when hybridized orbitals overlap. Multiple bonds, pi bonds, form when pure p orbitals overlap. So whenever you see a single bond connecting 2 atoms, you know that it formed by the overlap of hybridized atomic orbitals, okay? So whenever you see an atom with multiple bonds, you know that it formed by overlapping pure p orbitals, all right? So, hey, in case you were wondering, that is why an sp hybridized atom can only make 2 sigma bonds, because it only has 2 hybridized orbitals, right, you guys? Remember, let's take a look at the drawing again. Okay, so single bonds can only be made by overlapping hybridized orbitals, okay? So, hey, when you look at an sp hybridized atom, he only has 1, 2 hybridized orbitals. That's why he can only make 2 single bonds, here and here, with this hybridized orbital and with this hybridized orbital. He can only